research focuses on diversification, and yeah, we had a great opportunity in PhenoRob to really get a very large trial designed and set up to answer one of the really urgent questions in diversification research, which is how we can deal with the very large complexity that is typical for these systems. So the topics that I'm going to cover in my talk are the multiple benefits of intercropping. I will show you some of the benefits, both from the literature or from my from our data from last year. I will then also try to explain the reasons for the complexity in intercropping and why that actually is a problem, and in how far this is a problem. And then finally, we will come to the very difficult question, how we can tackle this complexity, how we can deal with it, and how PhenoRob technologies and approaches might actually contribute to solve this problem. So intercropping is the simultaneous growing of more than one crop in the same field, and usually this is only just two different crops, and the photo here shows different cultivars being cropped in the same field, different cultivars of rice that really was done on a very large scale in China with a great effect on disease reduction. But usually we are dealing with different species in intercropping that are cropped together, and there are many known benefits of these intercropping systems, growing two different species of crops together in the same field in comparison to sole cropping. So I've listed here some of the benefits. Increased grain yield is one that has been shown in many studies, and I'm going to show you an overview of the distribution of these grain yield benefits in a minute. Also improved resource use has been shown in terms of water resource or nutrient resource use. Reduced disease incidence, as I said already, especially here in the cultivar mixtures, but also in species mixtures, has been shown. Reduced pest infestation has also been observed, insect pest infestation, for example. And also yield stability is improved in comparison to the monocultures. Also, sometimes we find that weed control is improved. That is a bit more variable than the other effects. But generally, we could say that there are actually multiple benefits from intercropping in terms of plant health, productivity, and resource use. And for actually going towards a sustainable agriculture, this approach of diversification, this intercropping, is actually a method that has been proposed many times and is suggested by many researchers as a way forward. However, if you look in practice, actually intercropping, especially in the temperate zones and in intensive agricultural, intensively cropped areas, is not so much taken up by farmers. The adoption rate is actually still quite low, despite all these benefits. And one of the reasons for low adoption rates is that diversification is just very complicated, and also these benefits vary strongly. And one very, let's say, prominent example of the variation of the benefits of the yield benefits of intercropping is shown here from a meta-analysis looking at the distribution of land equivalent ratios of different mixture experiments. And the land equivalent ratio basically quantifies the benefit in terms of grain yield of intercropping in comparison to the monocultures. Basically is the land that is necessary to obtain the same yield observed in the mixture from the monocultures. So if you have an LER a land equivalent ratio that is above 1. That means you need more land to grow the same yield as observed in the mixture if you grew these crops in monocultures. So you just need more land in comparison to the intercropping, which means that an LER above 1 just means a benefit of resource use benefit of the mixture. So we want basically high LERs that would be desirable. And we can see here that the median LER is above 1. Basically, we have benefit of 16% plus, yeah, but there's also a very large variation of these values. There are also quite a few values that are below 1, which means that there are several instances where the benefits are actually turning into disbenefits. So on average, as I said, there's a positive yield effect, but there's, as shown here in the graph, a large variability, and that means we need to understand the mechanisms behind this variability to actually make sure that we can transfer the results from one side to the other, from one condition to the other. But in addition, there's also another very important reason for the variability, and this is because in a mixture, in an intercropping system, the two partners interact very strongly. That is actually what we want. We want this complementarity of the partners, but they also compete with each other. And if one partner becomes dominant and competes very strongly with the others, or with the other partner, it suppresses the other partner. And then this imbalance leads actually to a deviation from the desired proportion of the partners in the mix. And that if you sow a 50-50 mixture and you actually get an 80-20 outcome in the yield, then this is not what you would actually desire. So, but because of the nature of competition, it is often observed that the dominant partner becomes ever more dominant and suppresses the weaker partner, so that the difference between the partners in terms of proportion in the mixture increases over time, over the season. And this is not what we would like to see, but we would like to have a balance of the partner, of the two partners in the mix. And this is really what is so difficult in intercropping, to obtain this balance. So going back to this question of variability of the mixture effects, there are various sources of variation that have been shown in many studies, and typically we see that intercropping systems are compared against the monocultures under different accompanying further additional factors. Usually this is one or two factors that is included in the study, and that means that we gain some experience about the interaction of intercropping with other agronomic or also environmental factors. One source of variation for the benefits of intercropping is the species of the cereal or the species of the legume. Depending on which species you grow, you will find different benefits. It also depends on the genotype of these partners, but also on the management, for example, sowing density, row spacing, spatial arrangement of the partners, and the inputs such as fertilization, irrigation, or plant protection, and of course also the site conditions. So this is all known, and what is perhaps less known is that all these factors may also interact with each other to produce even more complexity that may explain some of the variation we see in intercropping benefits. So the performance of mixture and its relative advantage over the sole cropping is influenced by a large set of factors and all their interactions. So the question when and where is which mixture best in terms of agronomic performance, also environmental performance, this apparently very simple question is very difficult to ask because of all these different factors. So I will give you one example that is the result of meta-analysis performed by Döring. So this is a paper that we want to see very soon. So again, Döring took as a performance indicator the land equivalent ratio, which basically says how large is the benefit of the mixture over the monoculture. And 69 studies went into this analysis. And this graph is a bit complicated, but I will go through it slowly. So first of all, we see this familiar distribution of the LERs over the different values. So again, we see and can confirm the variability of the LER. Also, the average, the median value is above 1, which confirms the general average benefits of the LER. But in this main graph, we see the variation quantified depending on the genotypes that were taken. And of course, if you take many different genotypes, you cannot just look at the individual genotypes across many studies because these will change depending on which study you have. But what you can see is what is the largest difference between the different genotypes in terms of mixture benefit, in terms of LER. So this would be the range, so the difference between the maximum and the minimum. So basically, what is the worst and what is the best variety in terms of LER, and what would their difference be? And you can see that there's actually, depending on the number of genotypes that were going into this study, there's quite a large variation in the LER. And another example here would be the green dots. If you took the median of the LER of the different genotypes, that basically represents the situation that you take an average genotype, you just randomly select a genotype and determine the mixture effect. And in comparison to that, if you make not a random choice, but an informed choice, if you take the best one, what can you gain? And you can see here that in many cases, there are quite large gains from taking the best variety in mixtures over a random choice. And conversely, the red dots show what can go wrong if you take the worst variety in comparison to a random choice of varieties. Then, of course, you can lose quite a lot of the benefit in terms of mixture effects. So there's a lot of potential there, but there's also a risk to lose that potential. So that was also one of the reasons why we conducted a very ambitious field trial, where we thought, well, to deal with this complexity, let's do a very large field trial where we have many, many different combinations of genotypes and also management parameters. So as you can see here, again, the larger the number of genotypes, the higher tends to be the gain, the potential gain that you can make, of course, because they taking a random choice of genotypes, you may have more varieties that are, or if you take more varieties, then your chance that you get a super one are just increased. So we thought that we are going to test many different genotypes of one partner and also the others, and test them in different plant densities. Why plant densities? Because this will determine, we thought, quite a lot the competitive balance between the two partners. And also we performed this in different environments. So that resulted in a large number of trial plots, 320 plots per site. And of course, at this with such a big trial, you cannot measure all the usual parameters per hand in all these plots. So we complemented that with spatial and temporal resolution of crop data by using sensors and digital technologies. So this was performed at Wiesengut and Klein Altendorf, these two trial sites, Wiesengut as the organic farm and Campus Klein Altendorf as the conventional one. Although in this trial we actually had a low input scheme because we did not use any plant protection agents in these trials. So as for the methodology, we had 3 mixture levels, as is basically typical for any intercropping trial. We had the 2 monocultures, one would be the fava bean and the other was spring wheat, and then we had a substitutive mixture. This was combined with 2 different densities, a high density and a low density. Then we combined this with different fava bean genotypes. We had a short one, Mallory, and a long one, Fanfare, and 12 different levels for the spring wheat genotype. That was set up in a randomized complete block design with 4 replications and a small plot size of, or let's say a usual plot size of 10 by 1.5 meters at a row distance of 21 centimeters. And the partners were mixed within the rows. So this is a list of the different cultivars, and I've highlighted here the height. We selected the different cultivars mainly on the criterion that they differ in their height, because we thought that this will determine their competitive advantage over the bean, and we were curious to see if that has an influence on the mixture effect. Also to note that here's basically they all belong to the same maturity group, so that there's basically an equal time window when the mixture would be harvested. So this was set up in March 2020. Soil was sampled and then mechanical weeding took place at both sites. This is from the early season in last year, and we had a number of response variables. We looked at crop emergence, plant height, biomass, weed abundance, of course the total grain yield and some of the grain yield components. Also aphid infestation was measured, and further parameters were done measured in the selected treatments. That was complemented by digital imagery, regular drone flights over the trial, plus soil mapping after harvest. I'm going to come to that later on in our talk. And I'm going to show some examples of results here from these parameters that are marked here with an arrow. So first of all, just to confirm the benefits of intercropping here in terms of pest reduction, we can see here very, very clear and strong results on the aphids that are reduced in the mixture in comparison to the monoculture. The bean aphids infested only half or less of the plants in the mixture than in the monoculture. That was in that strength, perhaps even unexpected, but we can see here that we actually have a lot to gain from the intercropping. We also were not, or it was not necessary to actually spray insecticides, because in addition to the lower infestation, we also saw quite a few lady beetles and other antagonists of the aphids just munching them up, so that the population density was far below the economic damage level. So there's a strong reduction of the black bean aphid infestation through the intercropping. And then I would like to show you some examples of grain yield effects. So this parameter, the relative mixture effect, is related or similar to the land equivalent ratio, but it's slightly different. But the idea is the same. Basically, you compare the yield in the mixture against the yield in the monoculture. And what I've plotted here is the total dry matter yield in the monoculture. So the dry matter was cut during the season. So the whole plant basically taken to the oven and dried. This is mid-season, I would say, in June, and close to the end of the season, perhaps even. And here's the relative mixture on the dry matter. So what we want is basically to be up in this upper right corner, where we've got a high reference yield of the monoculture and a high relative mixture effect. Whereas in this corner, we would not like to be so much, because that means a low reference yield plus also a negative mixture effect. And what we can see is that basically here on average we get a positive effect of the mixture, but there's also, again, as I showed you in the previous slides, a lot of variation. And if we do the same graph for the grain yield, we can see actually that the sites are now becoming very different. We can see here that the Wiesengut, the organic side, the points have moved up, so the mixture effect is higher than before. And also we can see here that the points for the grain yield relative mixture effect at the conventional or low input side, the variation has gone smaller, but also it's more around the zero line, which means the net effect has decreased. So if we average these values, we can find that at in mid-season we have a positive mixture effect at both sides, and at the end of the season, in terms of grain yield, the positive mixture effect remains at the organic side, where we have also a lower mean yield, and disappears at the higher input side or at the conventional side. Yeah. So again, but we can also see even at the conventional side there is large variability and the potential to actually select those treatments that may show a high or higher relative mixture effect. So we asked ourselves, maybe can this be related to plant height? And again, this is the relative mixture effect, and this is plotted against the plant height of the wheat. But this seems to be only an effect of the site and not so much of the height itself. So we would expect that the plant heights at the conventional sites are slightly higher than at the organic site, because there's more resources for the wheat plants. This is the case, but also within the site there's actually no significant relation with the mixture effect. So what we would have expected would have been that perhaps the smaller wheat varieties would lead to a higher mixture effect, because they do not suppress the beans so much. And one way of displaying the dominance of the different crops is to look at the partial land equivalent ratio. That's basically how much bean was there in terms of grain yield in the mixture in comparison to the bean in the monoculture. And again, we do not see any clear relation with the plant height. So that must be something else in the differences between the genotypes that actually drive the mixture effects. So here again is displayed the different PLERs for the bean and for the wheat. So this is quite a common way of displaying mixture results, so that we can see here everything that lies above this this line here, this diagonal line, everything that is in this region here would have a land equivalent ratio above 1. So all these points here are basically doing well, whereas all these points here in the lower corner are not so performing not so well in terms of mixture effect. And also this diagonal line here, the broken line, shows basically the dominance of the partners, everything that is in this half of the graph means that the wheat is dominating, whereas here in this half the bean is dominating, and we'll see clearly that the wheat is dominating, especially in the especially in the conventional side. This is also confirming what we know from the literature. The cereal is often dominating. So what we would like to have is a high value here in this direction, and basically a small deviation from this angle, from this broken line. And we can see here that we can still do better, but there's also a variation that shows selection might be possible. And this is the same then on the grain yield, where all the results come a bit closer together. And also, perhaps interestingly, the bean dominance at the organic side is stronger than, or the wheat dominance, perhaps to express it this way, the wheat dominance at the organic side is smaller than at the conventional side. This is probably in interaction with the nitrogen dynamics at the site. So we asked ourselves as well, how reliable is the performance of the different genotypes across the mixtures and the monocultures in terms of the mixture effect. And again, we use the land equivalent ratio, here expressed as ranks. So basically, we have all these different wheat varieties plus 2 cultivar mixtures of these 10 varieties, and basically 1 means within this row, within this column, the Lennox was basically the best in terms of LER, and Jasmond was the worst. And interesting now is the question how the ranks are distributed across all the other factors, and we see that there's not a lot of consistency. That seems to mean that there's a lot of complex interactions happening, and at this moment in time we're not completely understanding what lies behind the individual performances of the varieties in terms of mixture performance across all these different conditions. So we can also express the variability in another way. We performed an analysis of variance and basically measured the contribution of all these different factors and interactions to the total variance of, in this case, the relative mixture effect on the grain yield. And we can first see that the site effect has the largest contribution. And there's also quite a large contribution from the residual, so that means the block and the error. But all this is basically management. Yeah? So quite a large chunk of the variability can be explained by management and genotype and their interactions. But site is the dominant factor, and if we then separate the sites and do separate analysis for these, we can see that in this similar graph where we have separated the different sources of variation on the mixture effect of grain yield, we can see that there's a lot of variation that goes to the interactions between the different factors, which means there's just a very large complexity in the trial. So understanding that is quite a challenge. So how can we deal with this complexity? How can we actually make sure that we select the best mixture in a given situation? And one approach here is to map the soil properties within the site to understand the underlying soil variability, especially for the organic side. That is an issue. And therefore, Daniel Pfarr, as one of the PhD students in this work package, in this CP, mapped out the mixture area at the Wiesengut with the geoelectrical devices with a PXRF information and the gamma spectra. So this is still, let's say, at the beginning. We still need to develop ways of interpreting these data in a meaningful, ergonomically meaningful way. But as you can already see from this map, there is quite some variation that we hope to connect up with the results from the Wiesengut. Another possibility is to obtain data, high spatially and temporally resolved data from the crops themselves, and that was done through various RGB pictures. And one approach here to understand the crop growth dynamics is or has the aim of automatic prediction of the crop growth by multimodal machine learning using as input these RGB images. So we expect that we then will be able to predict mixture performance relatively early in the season, and also to understand a bit more what lies behind all these complex interactions that I showed to you earlier. So especially one question is important: when does the competitive balance between the partners actually shift? And we hope that we can get this analyzed after actually individual mapping of the plants, and annotation of the different plants in the next few months. So these are some of the methods that are used to actually analyze the data here. Another approach is here to use hyperspectral imaging. I will show you in the next slide what we aim to do with this, or some results of this already, but also to go underground, so to map or to quantify the root growth and the nitrogen dynamics in the mixture, to understand a bit more about the dynamics that go on. Of course, the root growth is not possible to be measured in all the different plots. As you can imagine, this is quite labor intensive, but at least we get, for some key treatments, for some core plots, we get a more complete analysis of the data. So basically what we asked there is, what are the crop traits that determine mixability? And I hope I don't disappoint you if I say, after 1 year of trial, we haven't yet completely answered this question. So this is from the previous approach here, the hyperspectral imaging, where we can already relate the biomass to various spectral images. And then we hope that we can get a clearer understanding of the, especially over time, then how and across the large variation that we have set up in this trial, to get a clearer understanding of the interaction between the different partners. But perhaps as a last point, how can we deal with this complexity that I've shown that is happening in intercropping? Maybe it's a completely different approach. It's the centralized trialing of mixtures, not doing this at one location only or two locations, but doing this across many different farmers' fields. That would be an approach that would need to be farmer-led, and also maybe supported by value chains, so that there's some pull as well from other partners here in this in the range of stakeholders that are interested in actually making agriculture more sustainable. Then this could be supplemented perhaps with remote sensing to obtain data, which is perhaps a bit difficult for individual farmers to do this on a regular basis. And then we could join up the data and the experience by strong networking. This is at the moment, I think this is not done, at least not in Germany. But what we can gain there is very large and complex data sets that can be analyzed to understand a bit more when which mixture is best. There's of course a challenge in the data analysis because that's highly unbalanced data. But I think we are with the project here, with the use of artificial intelligence and machine learning, we are trying to at least contribute to that problem as well. So with that, I would like to conclude, and I thank you for your attention, and I'm happy to answer any questions.